Hi, my name is Muhammad Shukri Atika bin Lakadir and I'm gonna talk about the reaction engineering part. In reaction engineering part, we are gonna propose optimum reaction system for the conversion of palm oil meal effluent along with optimal operating condition considering economical and technical feasibility. The purpose of this paper was to give a review and evaluate recent studies in the field of producing biogas by determining the critical parameters and their impacts on the anaerobic digestion process. We study most of the articles and find out that there are four major reactions occur for producing biogas, which is the first one hydrolysis, second one acidogenesis, the third one is acetogenesis, and the last one is methanogenesis. There are certain conditions we must consider for optimal production. Active microorganisms require specific nutrients to effectively convert organic materials into biogas and reasonable environmental conditions. First, reactor. As we know, there are many types of reactor can be used as an aerobic digestion for this process, but CSTR is widely used in Malaysia with net methane production up to 62.5%. Second, temperature range of 25 to 45 degrees Celsius were chosen as preferable temperature because of strict temperature control, and lower temperature rather than thermophilic temperature reduce the cost needed for this process. Third, optimal pH are 5 to 7, which is not acidic. Too acidic will inhibit methane production in the biogas. Next, a mixer will maintain the uniform environmental conditions and pH by distributing buffering agents throughout the digester. Moreover, hydraulic retention time are 15 to 30 days, where higher HRT means higher production of gas but higher cost to maintenance. There are some examples of nutrients that are available for efficient biodegradation are phosphorus, nitrogen, and trace elements, which is micronutrients. Lastly, methanogenesis are commonly considered the most sensitive to toxicity of all the microorganisms in aerobic digestions. The toxicity of H2S, NH3, and VFS always depends on pH. In conclusion, this paper presented a summary to the design parameters of the biogas production plant, the available monitoring and controlling technologies of the anaerobic digestion process, and the significant environmental conditions in the reactor, as you can see from the figure. Hence, we agreed on the use of CSTR, mesophilic temperature range, pH of 5 at reactor 1 and 7 at reactor 2, use mixer, and hydraulic retention times are 30 days to maximize the production of biogas production. That's all from reaction engineering part. Thank you.
Hello, ladies and gentlemen. My name is Amar Hussaini, and we will proceed to the second section, which is process modeling and simulation. In this section, Kelvin and I will explain to you further about the process model and the simulation of the reactors. First of all, the introduction. There are four objectives to be achieved at the end of this project, which are: first, to develop mathematical models for the mass balance, component balance, and energy balance that enable us to determine the change of molar flow rate and the concentration of component species and the change in the temperature of the reactor. The second objective is to simulate the reactor simulation by using Aspen HYSYS. Third is to validate the simulation by comparing the manual calculation from CEB 2043 on the total molar flow rate of the final outlet and the final outlet of molar flow rate for methane and carbon dioxide components. And the last but not least, to analyze the effect of inlet pressure, inlet temperature, and the inlet flow rate on the reactor performance. Next is the dynamic mathematical model development. In this section, there are three balances that have been developed from the two reactors, which are first, the mass balance, second, the component balance for each of the chemical species, and lastly, the energy balance for the two reactors.
Hello everyone, I'm Xiong Jazen, and today I will be explaining the simulation which we have completed through the Aspen HYSYS software. So this is actually a steady-state reaction process which converts palm into biogas. The parameters of the simulation are based on process parameters which were defined in the reaction engineering segment. So the simulation involves two CSTRs and two product streams. So the fluid package that was used in our simulation is the GCEOS fluid package, which is the generalized cubic equation of state package. This package was chosen due to the fact that it allows the user to actually add their own parameters, and it is also useful for when the user needs to build their own model. On this slide, you can also find the component list, which includes all the components that are involved in the simulation, which are dextrose, H2O, water, ethanol, acetic acid, carbon dioxide, hydrogen, and also methane. And on this slide, I will be going through the reactions that were used in the simulation. So in the first reactor, CSTR-100, two reactions occurred, which were hydrolysis and acidogenesis. However, only acidogenesis was simulated in this simulation, and as you can see, the details of the reactions are stated here for your reference. And in the second CSTR 101, the reactions that occurred were acetogenesis and also methanogenesis. Both the details of both reactions are stated clearly here for your reference as well. And on this slide, we will actually look into the product stream conditions, which is what we are really interested in. And all the necessary properties and also parameters can be found on this slide. The composition of the product stream can also be found here.
Next is the simulation validation with the manual calculation. From our findings, first is the total outlet molar flow rate percentage difference is 13%. Second, the outlet molar flow rate of methane is 103%. Third, the outlet molar flow rate of carbon dioxide is 31%. So in conclusion, the overall simulation result is reliable since 30% is less than 15%. However, the individual component result is not reliable since 103 and 31% is more than 50%. Hence, it is not reliable. There are reasons why it happened. First, the assumption of the conversion for the manual calculation is 70%, while the simulation is 94%. So this difference in the conversion percentage may result in the variation of the outlet molar flow rate. And the second reason is the state of the manual calculation is assumed to be dynamic state of the reaction, while the simulation is assumed to be in a steady state of the reaction.
Hello once again, my name is Xiong Jazen, and I will be explaining the sensitivity analysis, which aims to investigate the effect of feed stream pressure, feed stream temperature, and feed stream molar flow rate on reactor performance. Firstly, we will look into the effect of feed stream pressure on the reactor performance. On the left here, as you can see, an increment in pressure elicits increments in the mole fractions of methane as well as carbon dioxide in the product stream. Whereas on the right here, as you can see, an increment in feed stream pressure elicits little to no change in the heat flow within the reactors, and therefore we can conclude that the performance of the reactor has been slightly increased due to the fact that the mole fraction of the desired product has been increased. And next we'll be looking into the effect of feed stream temperature on reactor performance. And as you can see here, it was determined that the increment in temperature resulted in no changes in the mole fractions of any of the components involved in the simulation. However, the increment in temperature did cause a huge fluctuation in the heat flow in the first reactor, CSTR 100. And this is largely due to the fact that due to the endothermic nature of the reaction that occurs in the reactor, which favors a high temperature condition. And regardless of this change, all other parameters remain the same, and therefore it is concluded that the the feed stream temperature has insignificant influence on the reactor performance. Last but not least, we'll look into the effect of the feed stream molar flow rate on reactor performance. It was determined through the case study that an increment in feed stream molar flow rate results in the decrease of mole fractions of methane, which is a desired product. And this is largely due to the fact that there is a decrease in retention time, causing inefficient reaction as a result of the increase in feed stream molar flow rate. And as you can see on the right here, the conversion in the reactor in the second reactor, CSTR 101, has also drastically decreased, which is indicative of the negative impact of increasing the molar flow rate of the feed stream. Fluctuations in the heat flow in both reactors were also observed as a result of an increment in the molar flow rate of the feed stream. And conclusively, it is determined that increasing the molar flow rate of the feed stream negatively impacts reactor performance, as there's a drastic decrease in conversion in the second CSTR, as well as a overall decrease in the mole fraction of the desired product, which is methane, and also an increase in the mole fraction of undesired product, which is carbon dioxide.
Last but not least, in conclusion, for the process modeling and simulation, all the objectives are achieved at the end of the project.
Hello, my name is Siti Nurziana, and now me and Amiratul Husna will explain about the selection of separation process units. Firstly, the biogas mixture of methane, carbon dioxide, hydrogen sulfide and water will undergo adsorption process using silica gel. Silica gel will act as drying agent to remove the water molecules. Molecules of water will adhere onto the surface of silica gel. Scheduled regeneration of adsorption bed can be done by altering the temperature and pressure of the system. After removing the water molecules, the mixture is then passed to another adsorption unit using activated carbon. Here, granular activated carbon as the adsorbent will absorb the adsorbate hydrogen sulfide molecule from the mixture. However, the hydrogen sulfide is poisonous and corrosive, causing the regeneration is almost impossible. By the end of this unit, the mixture of methane, carbon dioxide and small amount of hydrogen sulfide is then passed to the next unit. In the next and the last unit, it is proposed to implement membrane separation unit to remove carbon dioxide. Here, since methane is a bigger molecule compared to carbon dioxide and hydrogen sulfide, therefore methane will be retented and does not pass through the microporous hydrophobic membrane. On the other side, amine solution acts as sweep to absorb permeates carbon dioxide gas and hydrogen sulfide to ease the flow of the purification process. As the maintenance and safety precautions, there are few important points to be kept in control. First, corrosion monitoring and inspection must be done regularly to ensure no corrosion that can block the separation process. Next, a leak detection and alarming system is needed for alert if there is any unpredicted leakage. Also, frequent and scheduled regeneration process is needed to ensure an optimum operational life of the adsorbents. Last but not least, backwashing and chemical cleaning of membrane separation is needed to remove accumulated contaminants in the system. For the challenges and solutions, we figured out that the presence of oxidized water can block the pores of activated carbon. Therefore, we propose to have the adsorption using silica before the activated carbon to remove water. Secondly, we all know emissions of carbon dioxide to the environment will cause air pollution. Therefore, a sweep using amine solution is proposed to absorb the acidic gases to reduce its environmental effects.